Hi, folks. We're going to go ahead and get started, so please grab your last bite of food and have a seat. So I'm Mike Seaman. I'm the new chair for the San Francisco Bay PELS chapter. So first I'd like to thank Brian Zonstecker in the back with the beard for his hard work over the last 2.5 years getting this chapter from basically nothing to where it is now. And I'll talk a little bit about that quite soon. So this chapter won 3 awards in 2017. The Santa Clara Valley Outstanding Chapter, the Region 6 Outstanding Chapter Award, so that's all of the Western US, and the Best PELS Chapter in all of the world. So that's quite an achievement. 2018, we were disqualified from all these awards. You can't win them 2 times in a row. So that's where we are now, and hopefully in 2019 we'll have a good start as well. All right. So tonight's talk is titled Prognostics and Health Monitoring in Lithium-Ion Batteries and Capacitors Using a Physics-Based Modeling Approach. I'll give an introduction to the speaker in a little bit. But I'd also like to thank our co-sponsor, VTS, or Vehicular Technology Society. And finally, thanks to our venue sponsor, Texas Instruments. And Simon over there is our TI contact there. So thanks, Simon. We have a new set of officers. Chair, and then Sushil, can you stand up? Here's our new vice chair. Ed is our continuing secretary. He's over here. And Faye, let's see, is Faye here? Well, he's our new treasurer. And all the other officers, please stand up as well. So we have a number of members at large, and all these guys help us out significantly over the course of the year. All right, so I'm going to give it to Samuel for a second to do a quick power sources segment. This is looking at, I'll let him talk about it for a second.
Hi, I'm Samuel. Today, I'm going to just introduce, one book and then some resources, online. Just a little bit of, background. I wasn't being trained as a electronics engineer. I was being trained as a industrial engineer. And then when I get to the Silicon Valley, I started, working in the power IC, industry. And that's how I started, to learn, how to do, power supply design. So, therefore, some resources, that I can get, online or, from the supplier, I find useful. And that's why I want to introduce it tonight. One is this book, from Worth Electronic. It's a book from a component distributor, but then they did a good job in making this book, a manual, and also inside, there are some design methodology and also applications. And the most interesting thing is there's one dedicated, chapter that talk about, how to model, hysteresis and magnetic losses, and then how to build the model and put it back into the spice, that you can use. Of course, there are some commercials, with, it's a inductor and coil and all these component manufacturer, and then they introduce their products and then tell you that they are models, from them that, you can use. Okay, go to the website. You can order it online. It's €49, but then my company uses a lot of the, their components. So when engineer, talk to them, they usually send it to you, yeah, for free. Interesting. I got mine in this event. One time they came here, to do promotion, on their company and also, their services. And then there was a lucky draw, and then I got this, from a lucky draw. Yeah. So if you care to, take a look, yeah, please. Okay. So the other website I like to, introduce is the linear, technology LT Spice in the website. That web page has got a lot of good information and also, again, design examples and things like that, for people, to get ideas. And then the next one that I, like to bring up is the Texas Instrument Web Bench. In fact, I encountered WebBench more than 10 years ago, slightly more than 10 years ago. It was still a newly launched service from National Semiconductor. And then in the beginning, it was just very simple. You input your power input and then your output condition, and then they introduce a few integrated circuit from National Semiconductor. But over the years, it improves so much. Nowadays, when you input, these input and output power, parameters, and you can specify, whether you want, power factor control, and things like that, active or, passive. And once you press the button, it generates a whole series of designs, for you to consider. Isolated, non-isolated, with, power factor, correction, active, inactive. And also, more than that, there are some, data, modeling and give you, the input-output, characteristics, of each of the design already. So it's very good, for ideas.
Thanks. All right, so a couple more things to say. Are you an IEEE member and have been in the field for 10 years, including some of the time you've been a student? If so, you might want to consider being a senior member. It has a few benefits, namely recognition. Your boss gets a nice letter too when you get a senior member. You get a plaque. You get a $25 coupon for IEEE swag, and some other stuff as well. Our SCV section holds quarterly events where all the senior members or people looking to become senior members and senior members already get together. I think it might even be here, but it's local, and you get to have interviews with people, and you can find the 3 senior members to help you advance. So we'll keep you updated on that if you come to our future events. All right, here's our website. I won't make you remember it. You can just Google for SCV PELS, that works fine too. And then it has all of our future events and the slides from past events as well. eGrid's a great place to see where future talks are and other IEEE related events. So egrid.biz. And finally, please silence your phones, and if you have to take a call, please step outside before answering. All right, thanks for coming. So let's welcome Dr. Chetan Kulkarni is a staff researcher with SGT at NASA Ames Research Center. His current research interests are in system prognostics and health management related to modeling and simulation of hydraulic and electromechanical actuators, aircraft, electrical power systems, and in the area of developing component-level physics-based models for prognostic applications for engineering systems, lithium-based battery technology, cryogenic fueling systems, small and cube satellites. He graduated from the Department of Electrical Engineering Computer Sciences from Vanderbilt, and a BE from University of Pune. He's authored more than 60 publications, including journals, conferences, book chapters, along with several Best Paper Awards. So let's welcome our speaker.
Hello? Okay. Good evening, everyone. Thank you, Michael, for the introduction. And I would like to thank for the invitation from Sushil and Brian and Antonio for inviting me to the talk, because that they gave an invitation about couple of months back, and we had a good interaction first. So I'm meeting everyone for the first time. So, and I'm meeting Antonio after almost 6 years. So that was nice. So my talk will be more on the prognostic and health monitoring for systems. So the work what I do is more into developing physics models or the first principles model for different systems. And some of the work what I did was on lithium-ion batteries and power electronic systems. So capacitors was one of the work, one of the components what I looked into during my thesis work, and I continued doing that. I'm part of a bigger group at AIMS, so the talk is a collaboration of all the work from the different members of our team. So I'd like to thank every one of them, because I've interacted with them back and forth for a long period of time. And Kai Gobel is the head of the Prognostic Center of Excellence at AIMS. He's the one who started the whole center, and then that's what we have been part of the center for the last several years. Okay, so I'll talk about introduction, basic introduction of what prognostics is. I'll look into what model-based prognostics is, because that's something I'm not sure. I was not sure of the crowd or the attendance of how they will be. So I thought I'll give an introduction of prognostics, like a basic understanding of that. And I'll look into different research tools, and also talk about a few examples. So I had several examples in my slides, and I'll skip some of them, but the slides will be shared, so you can have more information on that. Most of the, as we go into the aircrafts which have more and more electrical systems on board, we will see them as both as purely electrical aircrafts or hybrid variations of those. And most of the UAVs are being powered with an electrical powertrain, and that's where we have seen that most of the health monitoring is a requirement, or that needs to be done, because we will have how do I use the laser? Yeah. Oh, yeah. Oh yes, the big one. Okay, sorry. To include most of the electronic systems, you have vehicle controls, you have communications, navigation systems. Everything is being powered, either has a lot of electronic systems on board, or they have part of bigger systems. And you have MOSFETs, IGBTs, you have capacitors. So these systems, it has been looked at that they don't degrade or they don't fail. But as per some of the studies what we have done in the past several years, we have found that these systems do degrade over the period of time, and it's required that we monitor these systems as they become more and more as part of the whole hybrid framework, or the whole electrical aircraft airwork. And to know that how the systems deteriorate, we need to know how the components degrade or how they fail. And that's a very key requirement, because if you need to make a prediction of when a certain thing is going to fail down the line, you need to know what its current state of health is. You need to know what the operating condition is, or what the system is operating under, and then try to predict it down the line. There are different ways where researchers have looked into, and I'll talk about both of the ways, and then why did we choose the model-based approach for that. These are some of the examples of the applied applications where we have. So you have purely, you have some hybrid aircraft. So some of the new aircrafts are hybrids, but some of these aircrafts, they are purely electrical aircraft. So the Edge 540 this is the aircraft what we have applied most of our battery algorithms on, and we have been doing that at Langley, NASA Langley in Virginia. So that's the aircraft currently what we work on. a basic definition of prognostics, what do we have? So it's basically that something that foretells or something where you can predict in the future. That's the goal. But as part of the PHM community or as a community, what we see is that how do you estimate the remaining useful life of a system or of a component? So you are at a certain state, and then based on that, how do you come to know that how much time is left in the usefulness of the component? And that's the prediction part what we try to explain. And that depends, as I said, mainly on your future conditions, your operating conditions, what were your past operating conditions. Also, a lot of it depends on your environmental conditions, your load, your operating systems conditions, which can depend on either of these. We looked at why we need to do prognostics, but now we need to look into why you have to do model-based prognostics. So model-based prognostics is basically you have a given model which is basically any which has a system input and a system output, and you have a basic system model. So the reason to use this is either of the framework can be developed based on what your model is. So you can have a model of a battery, you can have a model of a mechanical system, you can have a model of a composite or a structural system, but the framework remains the same. So there is no change in the framework. So the whole premise of the developing such kind of models is you keep your framework as generalized as possible, and then try to develop models where you have certain system inputs, you have certain system outputs, and a model is based around those things. So they can be applied to any class of systems. So it doesn't matter if it's an electrical system or a mechanical system or a composite system. This is the basic, just to give a basic idea that wherever you are in your system state, you define a damage threshold. So that damage threshold can be depending on what type of system you use, and at any point t, you then try to make a prediction that when my system is going to fail. So that's a very basic idea what we try to do, and that can be done at each and every, it can be done at each time step. It can be done at several time steps down the line. So a prediction very early in life probably has a lot of uncertainty because you don't know what the loading conditions are, how the system is going to behave. But as you go closer and closer in time, and that's you make a prediction, probably you are able to make a better estimate of the system because you know what the system state is, and then that's the place where you can make a defined category or the defined end of life estimate. And that can be a soft threshold, this is a hard threshold where you have a single applicable line, but you can have a soft threshold where you can have a bounce around it. So it can be a 5% bound or a 10% bound around it. And whenever you make an estimate from time t, that's till the end of life, that's called the remaining useful life, and that can be different at different points of time. So as you get closer and closer into the as you get closer and closer in the end of life estimate, your RUL will keep on changing or decreasing. This is the basic example of an illustration of why we need to do prognostics or what's the requirement. So, for example, if you have an electric UAV or a small octocopter which needs to do basic missions where it has to go around these 4 objectives, and at some point of time you have a discharge or a fault which is injected in the system. So once a fault is injected, if the system is able to know what's the type of fault, so you do a fault detection, and then if it's able to make a prediction that based on the fault magnitude and the type of fault, probably the mission is not going to get completed with the given flight profile. So in that case, a decision can be taken that either it skips objective 4, but try to return to the home base in the safest manner as possible, or if that is something which the flight plan doesn't occur because probably that would require a higher energy requirement. It can change that to just doing objective 4 and skipping objective 3. So that everything depends on what type of flight path it has, how much energy is going to be consumed, and what the fault type is. So if the fault type is something which is not a high magnitude fault, then probably doing objective 3 and coming back to base, that would be the one of the decision making part of it. Or if the fault is at a higher magnitude, then probably doing an objective 4 and then returning back to base would be the right thing to do. So that depends on how the algorithm is developed, and it gives the feedback to the system. And that's how one can take in the prognostics output and then try to replan this. This is an example for a single flight, but the same thing applies for your maintenance systems, because if you have to do a maintenance on certain systems, if you know something is going to fail probably a month in advance, you can actually don't have to do a time-based maintenance, but you can do a condition-based maintenance. You can apply that to certain autonomous decision-making also. So this may be a manned mission, but if you have unmanned missions, in that case also you can take some autonomous decisions. So it depends on what type of system you have, and then try to apply it to those accordingly. What does prognostics help in? It helps to maintain strategies, and instead of that, as I said, instead of time-based maintenance, you can do more of a condition-based maintenance and try to take decisions based on what's the state of the health of the system, then based on what time it has been operating. You can do, that helps in optimal scheduling. You can have your spare parts or your parts requirement shipped accordingly. Reconfiguring the systems, you can prolong the component life. So prolonging component life is something where if you know that the device is degrading, but if it's something which can still sustain for a longer period of time, you can actually have your loads change on the system, which will then prolong it to at least reach a specific time where you can take a decision to change it, put it under maintenance, or try to add a new redundant system to it, something like that. So it all depends on how you look at it. So finally, it comes to an optimization problem where you take a decision that what things I need to do. So that can be on a shorter scale, they can be on a longer scale. So something which is on a longer scale, probably you can have a human in loop, but something which is on a shorter scale, probably if some decision has to be taken within like a 10-second or a 15-second, probably a human in loop is not the correct way to do it. But if there is something like an advanced scheduling for maintenance or parts to be procured, then that's something where a human in loop can come into picture. So that's also a different way where you can apply the whole framework. So again, the same, try to get it in the whole picture of it, that this system cannot be necessarily a two-dimensional system. You can have multi-dimensions in it because you can have different variations of it. So that's why you have your system state, and then at any time t, that time t can be defined by the user. So you don't have to have it at each time step, but you can do a prediction every per day or per week something, because if your system is degrading at a very slow pace, you don't have to do a prediction every minute or every second basically. So that depends on how you look at the system. And the schematic, as I said, is not a single system doesn't degrade in a single dimension. You have multi underlying phenomena which are occurring, and so they all can contribute to how your system is going to be in a specific health state. And the example can be applied to lithium-ion battery. So you have your cell voltage, and then at any time t. So this is some example of your the cell phones what we use. So you have at the end of the early in the morning when you charge your phone, probably that's where everyone is, and then it always tells us that okay, it will last for like 4 hours or it will last for like 8 hours. And how does that calculation is done? So in most of the time, you get a very rough estimate of it. There's no accurate estimate because the algorithm will doesn't take care into most other things like what apps you are going to use, or are you going to see video for most of the time. So those things are not known for the app. But if you know something in advance, or that information is known in advance, probably that estimate can be a bit lower, and probably a decision can be made based on it. So, and this voltage threshold, in most of the cases, it's very much user dependent. Like someone can degrade their battery up to like, if this is a single cell, you can go up to 2.5 volts, but someone who is very conservative, they may say that, okay, I won't go below 3 volts and I'll get a cutoff around that. So that's very changeable, or that can be varied and based on how the user looks at it. What are the different algorithms? Because we saw what prognostics is, and what are now the different algorithms we are trying to look into, and what researchers are using. So most of them are reliability or database. So those are something which are based on the statistical models. So most of the, I would say the data sheets, what you get from the manufacturers, probably those are something what can be used, which are based on the statistical model. You have stress-based, where you use into, look into the environmental conditions. You have the temperature, loading conditions. So you can try to do some hazard models based on that. There are some condition-based, where you actually are trying to do individual component-based data-driven models. So there is no a single formula which is applied, because each component can degrade at a different rate. So then you try to do something like a condition based, because if you take a same phone, like everyone may have an iPhone or something, but if you buy it at the same time, the same version is the same, but the way you use it, it's absolutely different, because your temperature is just changing. Someone may be using it, charging it or discharging it like twice a day. Someone may be discharging it at once a day or something. So all those profiles are changing, and that's why you are degrading the battery or any system, which component which is there inside differently. So those are like something like a condition-based monitoring. So there, in that case, you will get a end-of-life estimate different for each and every component, though they come from the same manufacturer, they come from the same lot or something. And then there are two ways of doing it. So the condition-based monitoring, that's the way which is the path which is taken, and then you can do either data-driven, but then data-driven has its own pros and cons. So you have the system where the failure modes are, or you need to know what's the state of the system, and that can be done only when you are doing a lot of experimental data. So you have to do several experiments and try to get the data. So your model is as good as your data. So if you have almost all the spectrum of the operating conditions captured, then probably your model is good. But if you are capturing only a certain part of the spectrum, then probably your model is as good within that spectrum itself. And that's something it works for most of the things, because at times it may be very difficult to develop models, but in most of the cases where you are looking at a more generalized approach, these type of approaches always work. And you can use regression models, you can use some statistics, you can use some mapping like a neural network sort of thing. These type of models, they are gaining a lot of popularity now as we go into the machine learning and more of the data-driven approaches. I've seen more of work coming from this area recently, especially in the area of prognostics. And again, as I said, it has its pros and cons, because they are relatively easy to implement. They identify relationships which you do not look in a previous condition. So if you are able to look into a wide spectrum of operation, then probably you are able to match the relationships between these systems. But again, as I said, you require a lot of data, like you can, a lot of run to failure data. You require, there is an overlearning risk, because if you work in a very specific operating spectrum, then you probably may be overfitting most of that, but then you may not be considering the rest of the part which is outside that operating spectrum. So those kind of things may happen. And experimental work, Antonio knows it better, because we have been doing a lot of experiments work, and it's so difficult to get the data out of the system, so that becomes at sometimes very difficult for it. So once you have this approach, but then you have a physics-based approach to it, and that's something what we try to work on as a group, where we have looked into deriving first principles models, or something called as the empirical models. So empirical models are something which you don't go right to the first principles, but you can actually try to develop something which is close to the classical first order response. So basically, those need not be at the very finer level, but they can actually try to work out and give a very good indication how the system is degrading. And that, you can also have, in that you can have the finite element models, and you can have a high fidelity simulation models. But again, there is a time when you have to select some of the models which have to run on board. So if something has to be run at runtime or on board a vehicle, then probably in that case, if you have to have a first principles model or a lump parameter model that is relatively computationally less expensive than if you have a FEM model or a high fidelity simulation model. So in that case, probably that's not the correct model to choose when you have less computational power on board. So, and that applies to the data-driven methods also, where you can have a mapping or something where you have less computational power required. So there is always a choice, and both the methods what I discussed, they completely fit in the prognostics, the earlier framework what I showed, where you had the model-driven method. So you can either have a model derived from a data-driven point of view or the physics point of view. So you have the pros and cons for the physics-based model. So you have the results tend to be more intuitive in that case. So you because you know what the underlying phenomena is or what the underlying process is, and the models can be reused. So once you develop a model, so like something for a 18650 battery, you develop one model, it's a generalized model. So that you don't have to reinvent the model all the time. Once the model is done, you take a different manufacturer, you take a different type of, you put it in a pack, you put it in different combinations, you can still use the same model for it. So that's a generalized model, which is the key for developing such kind of, they are very difficult, or I would say very time consuming in development, but at the final, if your final goal is to have a certain way in which the efficiency of the model has to be increased, or the efficiency of the model needs to be tuned, then probably these are some of the one of the better approaches to do with. And then you can have like a Paris law, or you can have a Taylor model, corrosion model. So you can have different types of models which have been developed based on this. So coming to so now we have, we looked at what prognostics is, what are the different methods we can use, and now we'll come to what the model-based prognostics. So that's how I try to fit the part that we'll have look into what we have implemented, or something what we try to work on. So you have your state vector, so that's the, sorry. So you have your state vector, so that can define what the degradation process is, and then you have your R, which actually defines your, basically that's the remaining useful life at time TP, where you estimate what's your, the failure threshold. So you can define your failure threshold based on it. You can have your state vectors basically as an input to a Kalman filter, which will keep updating your state. You have your model, so you can have your input model, and then you can have your input parameters, which will then keep on forecasting the system health as we go in the future steps. And then based on what your failure threshold is, then you can compute your the remaining useful life for the system. And this process can keep on going. It can be if you have multiple components, if you have multiple degradation mechanisms, you can implement the same framework, and then those can work at different timelines. This is the basic example. So this is you are tracking your system. So you track it at a certain time step, make an estimate. So that's a certain time in the life. Once you update it, so if you update it after, as I said, you can update it depending on how your measurements are taken. So at the next update, you again have a better estimate what the state of health is, and then you try to make an estimate. So probably, as you see, the estimates keep on changing because the rate at which the device has been operating or the loading conditions are changing. So you have an update of the system and then you make an estimate. So that estimate keeps on changing, and as you go near and near, that's when you try to get a better understanding or you have less uncertainty into that system. So this is the overall methodology what we have implemented. You have accelerated aging data because to develop a model, you need to know at least what the underlying, you have to validate the model. So in the work what we have done is we actually have developed the test beds. We have developed hardware in loop test beds where we actually have aged different components. So we have aged capacitors, we have aged MOSFETs, IGBTs, we have aged batteries, we have aged pneumatic valves. Everything is the same. So you have those accelerated aging models data, and then you have your degradation models, and those degradation models are then used as a state space representation where you have the x and the y's, and then you estimate what the current state of the parameter is based on the current each parameter state of health and your state space representation. Then you estimate that how much is your remaining useful life estimation and how much is your health state estimation. So those can be then predicted at each time step, as we saw in the earlier plot. So this is some of the high level the efforts what we have been doing. So we have done looked into, as I said, into MOSFETs. We have looked into capacitors for the power supplies. We have looked into a lot of thermal aging for the IGBTs, and also on the battery degradation and the aging effect on the speed controllers, so electronic speed controllers, because they are a key part of the electrical powertrain. So we tried these different options, but the framework used behind this was exactly the same. So just the models were changing, or the components of the systems were changing, but the overall approach was the same. So you have your failure modes identified, because if you want to know how the system is behaving, you need to know how the system, the different failures are, because if you don't capture that as part of your model, then it becomes difficult. So if I know that my capacitance of a capacitor is changing and my ESR is changing, I need to know that it's related to something at the back end. So probably that's due to an evaporation of the electrolyte, or that could be some oxide formation due to which the capacitance is changing. So those kind of the first principles relationships are very important to know for the model building. Then you identify the precursors, so the precursors can be defined. So probably in some cases, someone is looking at capacitance as a very key precursor, but the internal resistance doesn't matter. So probably you can use that as a precursor, and it can change on operating conditions also. You develop your test beds, then you develop your models based on that, and then apply the prediction algorithm based on the top level approach what we saw. And this is the cycle basically. So you have your model development, you have your the prognostic algorithm update, you validate it under the observed conditions, then you apply it to the formulation of the model, because that's where you try to identify or look at what your hypothesis is correct or not, and then you do a validation experiments. And this is a cyclic process basically, because you keep on doing that as you try to upgrade your models. So basically you have you can start with a very basic physics-inspired model or a empirical model. So because you don't know how the system is operating, so you try. That's why you try to with a very basic model, and then you go try to iterate it over the period of time, where you can add more information to the model or more information to the system based on how the different experiments you have been doing and what results you have been getting. So this is exactly something what we have observed, and we started from a very like a lump parameter model, and then went to the very detailed model where we can look at how C's and ESR are changing independently. So this is the basic architecture. You have your system. So your system receives inputs and outputs Once it receives, it will identify an active damage mechanism. So once your system starts behaving odd, or it's behaving out of the way, that's where you need to identify that's what's going wrong with the system. Because probably if you have like your voltage, your current, your temperature, either of these three are changing. Are they changing due to independently, or they are changing because there is some effect on each other? Because like if you draw a lot of current from a battery, probably then that's the reason the voltage is decreasing. But if you draw additional higher current, then your temperature starts decreasing, or your temperature starts increasing. Sorry. And so you need to identify that which component is attached to what internal mechanism, and that's required to identify that is there a fault in the system, or do you need to make any apply the prognostic algorithm to that. So once that fault is detected, so you identify that fault with the FDI approach, then you estimate what my fault is. So I need to estimate what the magnitude of the fault is, because if the magnitude of the fault is very low, then probably it's still within the noise margin, probably that fault is there. But if the magnitude of fault is something which is high, then that's the example what we saw in the UAV example, where depending on the fault magnitude, you have to take that decision that do you need to change or replan your flight. So that depends on that estimation of the magnitude, right? How high the magnitude is. And then based on that magnitude, then you make a prediction and try to do a probability distribution for that. So probably that could be, depending on what the fault is, your probability distribution will keep on changing. These are some of the problem requirements, or what are the requirements. So you need a system model, you need the prediction inputs, and we have been seeing this. So there will be the state space, the state inputs, and you have the initial time, your prediction horizon, and the system outputs. This is the basic system model. So you assume that the system can be used basically with discrete time variables. So those discrete time variables need not be at every 1 second or every 10 seconds. They can change as per your system. So they can be different. You have a state vector as an input and your state vector as an output. And then you have sorry, I'm clicking the wrong button. So you have your process noise, because then we have to put that as a part of your Kalman filter framework. So you have to include these as part of the variables included in the model. And then you have your future trajectory, and then you have your process trajectory model. And then this defines basically the EOL will define that at what time k dash, whenever is greater than k, that's when you hit that threshold. So anytime before k is less than or equal to k, that's when it's 0. Basically, that means it's still not reached the threshold. The moment it goes beyond that, that's when you have the flag where it says, okay, I've reached my end of life threshold. The system needs to be changed, or you take that decision based on it. So this is how the first diagram what I showed, the plot I showed was a 2-dimensional, but this is more intuitive, like how the system will behave. So you are at somewhere at around k naught, and then at kh, probably this is the kh value. You can either be in a healthy state, so when you do a prediction future down the line, you can be anywhere on the path, because based on how your operating system is, the condition is applied, you can either be somewhere in the non-failure state, or you can be in a failure state. So you have to identify that, and that's the probability distribution what you get. When you do a probability distribution, you will have some of your paths which will be in the healthy state, and there will be some distributions or some of your points which will be in a failure state. So you have to, based on your state of the system, or the state of the health of the system, we can identify that are we in the failure state, or are we going to be in the non-failure state, any like k plus n steps down the line. And this is the basic algorithm what is used. So you set your initial state where you are, you check for failures, and then return the current type as EOL. So as I said, like when you return K, basically when K is 0, probably you are in a healthy state. So that means there is no failure required. But again, when you update your state, you check for the failure and then return your current time. And then this basically keeps on looping within till you reach that end of state. So wherever you are for K equal to H minus 1, you keep on doing this and try to identify when you're going to reach that end of life state basically. So applying it to the battery example. So you have your state estimation for the battery, and then you have your end of discharge prediction. But what happens, as I said earlier, that you have two different phenomena which are occurring in the system. So the first phenomena what you see here is for the end of discharge. So you have your battery. You want to know when it's going to discharge. But the other phenomena which is underlying is how the battery is aging also, because you have different aging. Your battery capacity is decreasing because you have been discharging and discharging because several hundred times. So your capacity is discharging. So the algorithm looks into giving an estimate for your end of discharge, which is for that specific cycle, but then also looks at the aging parameters. So the underlying phenomena is basically your aging parameter, and it keeps on making an estimation for those parameters also. So this is the state estimation. So basically you need to know what is the current state and its associated uncertainty, and the battery models, and you can use any of the filtering parameters. So you have your model, but you can use any of the, you can use an extended Kalman filter, you can use a particle filter, uncertainty Kalman filter. If it's a linear model, then using a Kalman filter is the best option to go. But the most of the systems are non-linear, so you have to use some kind of a mechanism where you transform that non-linearity to a linearity. So you use a extended Kalman filter or an uncertainty Kalman filter. We have been working on most of the time on the uncertainty Kalman filters, but any other approaches are equally good, and they are equally, there are a lot of researchers who have done that work. So the only reason to use it is relatively it's very easy to implement and tune, and then computationally UKF has been, in most of the examples what we have observed, that UKF is computationally efficient, because that's one of the points what I mentioned earlier, that how computationally efficient you are based on where you want to apply the system. So if you're using it on a high processors, your system and in work, probably a particle filter is equally good in that case. But if you have a small chip which is on an aircraft or a small UAV, then probably you are very constrained on how much computational resources are available to you. So in that case, these decisions have to be taken, that which model to use and then which process, which other filters to use. And then once you have the state update done, then you have to do a prediction. So the prediction basically is a represented, it represents the uncertainty which is selected based on the prediction algorithm, and the algorithm accounts for it, and also it defines the uncertainty based on your mean and the variance. So when you do a prediction, the prediction is based on just the model. So how good your model is, you will do a better prediction of it, because the Kalman filter or the particle framework doesn't come into picture in the prediction. You are just doing a Monte Carlo simulation in that case. So whatever your current state of health is, whenever you want to do an estimate, that the prediction part to the end of life, everything depends on the model. So how good your model is. So in that case, if your model is relatively good, you may have less uncertainty, but if your model is relatively, what you can say, a lower fidelity model, so in that case you may have a higher uncertainty. And that also depends on what your future loading conditions are. If you know your future loading conditions, then probably you will be in a very less bound, because then you know how the system is going to behave. But if the future loading conditions are absolutely not known, then in that case you have a lot of uncertainty, because your bounds are, they can be anywhere basically. So something like if you know a prior flight plan, then if you know the flight plan, then probably your uncertainty bounds are relatively less, because you know which weight points you are going to hit or which altitudes you are going to go, based on which then you are going to make the power consumption estimation. I just added this slide, but we can do the question answers later, right? So I'll just skip this. So this is the example what we have been working on. So it's a electric power system, propulsion system, where you have your lithium-ion batteries, you have your conditioning circuits and the driving circuits. The commutation circuit is basically the speed controller is on half-bridge rectifiers, and then you have your brushless DC motors. So most of the modeling work has been done on batteries, and where we have seen that due to corrosion or electrolyte formation or contact losses, you may see some damages there. Brushless DC motors, they have their own ways in which they degrade. So you have this internal resistance increasing or insulation damage, so that may lead to damages in the DC motors. And then speed controllers, you have MOSFETs and you have the switching the circuits, they have a fault, and that's one of the talk what Antonio is an expert on. So so MOSFETs, that's some work we have done earlier, and capacitors. So what we try to do is we did the work at different levels, at component level, and then we are trying to bring that at the higher system level, where we can see how each of the component or each of the subsystem has an effect on the whole efficiency of the operation of the powertrain. So this is one of the test beds what we have built. So this is an equivalent of what the UAV is. So it's exactly mimics what the UAV does. And this is the benchtop test bed what we have developed in the lab. So you have your the motors. These are the tandem motors. This is the load. These are the 4 batteries which actually operate the motors, and then these are the 2 ASCs. So since we have tandem motors, one ESC controls one of the motors, the other controls the other one, and then the 2 batteries power the whole system. So this is what we have on board, and the good thing about it is it's very difficult to inject faults in when the aircraft is flying, because it's safety-wise, we have to be very cautious that it doesn't have any effects on the aircraft, like probably if it's the safety requirements are met. So we came up with a more benchtop model, where in this case you can inject any fault. So you can have a degraded battery in the whole system, and then try to see if your algorithm detects that fault and then makes a prediction. So that way we can run these experiments like a couple of times in a day, but doing a flight, it takes a longer time because of all the background work what is required to do the flight test. This is I mentioned about the accelerated aging. So these are the more traditional ways where researchers have looked into how to collect data, because whenever you are doing most of the experiments, you know that okay, my system is good, and then you have some MTBF values which are attached to it, and then you take that as a face value and try to you implement that as part of your model. But if you want to do a thorough investigation of how the system is behaving through the timeline, then these type of experiments are something which are used. But again, in most of the cases, if I need to degrade my battery for my experimental purpose, and if you run it on nominal conditions, it may take me several years to actually come up with that model. And so these are some of the, from the reliability point of view, what experiments have been done. We try to take that, we took knowledge from there and try to develop our own test beds where we can actually capture the underlying phenomena of these the degradations or the failure mechanisms, and do it under this electrical, the high impact accelerated aging methods. So I'll skip this, sorry, because this is for the, I'll go to the last slide, because I'm not sure how much time I have, but. Okay, so, no, sorry. So, the two examples what I wanted to talk about was, one was the capacitors, because that's some of the work what I did as part of my research work, and then the other was of the batteries. So for the capacitors, if you have to develop a model, then you have to look at what the structure is, or how do you develop that model. So you need to know what are the two key criteria which define the degradation. So that's basically your equivalent series resistance and your capacitance, which define the health state of a capacitor. Then you need to get to know that what are the mechanisms. So you know, we know that capacitance and ESR increase, or ESR increases and the capacitance decreases. But then the whole fishbone diagram actually gives an idea that what underlying phenomena is related to a decrease in each of those components, or which enables the degradation the process. So this is something what we look through most of the literature, or we look through experiments, and then try to define these different underlying phenomena which relate to the degradation in the component. And these helped us develop the model basically. So we saw that recurring example where we were updating the model and validating it over the period of time. Yes. That's what we try to develop is, we had the non-ideal model, and then based on the experimental field, then you try to look into how the model behaves under electrical stress and how the model behaves under thermal stress. So you have different models for different degradation phenomena under those operating conditions. I'll not go to the mathematics because, but this is the whole mathematics what we actually come up with. Like, we have the model developed and then try to put that as a state space equation, and then that state space equation then was used as a dynamic model for the capacitance degradation. So basically you have, so this is your initial capacitance, and then this is the time-based variable which is based on the first principles of operation of the capacitor. Similar to that, a model was developed for the ESR, or the equivalent circuit resistance. So we have the D5. So basically you have your electrolyte resistivity, you have the correlation factor, and what is your breakdown factor. So those components define what your ESR is based on your operating conditions at any given time t. And then this is the implementation in the Kalman framework. So the main part what I want to show, okay, so this is the part where you try to see that the model for the EOS, or the capacitance degradation, how it evolved over the period of time. So you make an estimate at each point and then try to see how where you will hit the threshold. But just making an estimate, that's one way. But how good is your model, or how well were you making a prediction? So you have actually, this is one of the prognostic estimate, or the prognostic matrix what we have developed. So that was developed by Abhinav from our group, so, and the others. So this is basically an estimate, or the prognostic estimate, where the cone is basically indicating that how well you are within your estimate. So the dashed line is the mean, or that's actually the truth, and then the dotted lines are your estimates. So each of these estimates are actually these dotted dots at different time steps. So if you are within that, so in this case, this was alpha is 3, so that's basically a 30% cone. So if you are within a 30% cone, if that's your requirement, you are doing good. But if you are within your 10% cone, you can reduce that uncertainty in the output or your prediction, and then try to come up with this estimate. So just developing a model is good, but then predicting that down the line, which is a good estimate, or within the margin estimate, that's also a very key requirement, because you cannot just say, okay, my capacitance will go over the threshold in like 15 hours. But if that is plus minus 20 hours, that's a useless estimate, because that's not something what someone wants. But if you make an estimate which is plus minus 1 hour or plus minus half an hour, that's a good estimate. And that's something what this alpha lambda plots give you an indication that how good an estimate did you make it. And the similar estimate, you can do it for a degradation model for the ESR. So that's for the ESRs, and then we did it for the thermal overstress. So we had the same model, and then tried to look at how good we were estimating. So in the initial phases, probably we are off, but then as you go closer and closer to the end of life, you are making a better estimate of the system. And the last thing I want to talk about is the battery models. So the battery models, as I said, you can have different layers of them. So you can have a very basic a model which can be a source and a resistor. So that's a battery itself. That can be a battery, but it can be as detailed as this one, where you have your internal resistances, and then you can have your polarization constants and the rest of the systems connected. So this is the equivalent circuit model, what is used in the battery. And then this is the plot where it shows how well the battery model is fitting. So you have this is the measured value, and then you have the fitted value across it. So the model works well. It's one of the most used models in the battery community. But we went a step ahead and actually tried to develop a physics-inspired model. So that was where we tried to look into the different equilibrium potentials and then capture the contributions from the different sources. So that's something what we tried to look in this model, and that model also was able to perform relatively well. So considering the measured and the predicted values and how well the model performs. So this performed under a constant discharge. This was under an open circuit voltage discharge, and this was under a variable discharge. So this was actually on one of the UAVs what we had. So the model was tracking very well. So that means the model is able to make good predictions of how the system is behaving. And it was applied on one of the H540, and in that we had a requirement that you have to give a 2-minute warning to the pilot when the battery is going to discharge, because that's something what the pilot needs to know before he can make a landing decision. He or she can make a landing decision. And so we did an experiment where we looked into at the algorithm. So it will raise an alarm when the state of charge of the battery is at 30% SOC, and then that's when the pilot can take a decision to land the aircraft safely down. So and then we had to validate the algorithm itself, because you cannot just do that once and they say, okay, my algorithm worked well. But we actually did 23 experimental runs. So these are the 23 experimental runs what we did. And out of that, in some of them we injected faults, in some we did not inject faults. And we were close to 91% when the algorithm was validated. So you have different batteries, you have different operating conditions, because in some cases you had fault injected, in some cases the weather condition was not good. So, but all those things, under either of those conditions, the model was able to capture all the phenomena, and it was also able to make better predictions. So with that, I'll just end with the slides, because this is the data repository what we have with our group. So if anyone is interested to download any of the data sets or any of the models, they can download it. So you can go to the website. The slides will have that. But if you just look at Prognostics data repository, you may be able to download all the data from the file. So with that, thank you very much. I'll keep this so you can have it. Okay.
Thank you.
Okay, thank you so much.
We have time for a few questions.
Yes, sure. Yes.
Isn't one of the fundamental problems, though, you kind of mentioned some aerospace applications. If you look at, let's pick some examples. Generalized reliability models have been used in the aerospace industry for a long time. Yes. But then you go back and you look at the actual failure mechanisms that typically occur on missiles, rockets, and other highly stressed systems. In almost all cases, it's not the generalized model that ends up being a failure, but the devil's in the details, stress concentrations, thermal gradients,
right,
software errors, and all these other types of things. So the question is, if you were going to use a model like this, don't you really have to have a good understanding of the underlying material science? Because it seems as though part of the model is based upon having the data available, and that would say then you have to have an intelligent strategy for instrumentation of battery packs and other types of things, so that you can get down to the appropriate level where you can do the weighting, say, well, these are kind of irrelevant variables, and these are the real devils in the detail items that we need to pay attention to. Because if I start looking at the the number of variables. You could vary pressures, you could vary temperatures, you could vary process parameters associated with electrolyte thicknesses. I mean, you could go on, and by the time you start doing the multiplicative analysis, your matrices would grow so large it would become almost impossible to do the analysis in real time.
Yes, no, you're right, because whenever you want to do an estimate in the future, or you need to know what are the different phenomena occurring. That's why I said that doing a physics-based model is a very difficult part, because you need to know what all the underlying conditions or what the different conditions the system may undergo. Yes. Yes. Correct. Right. No, and that's why. So that's why the approach. The reason we have the data-driven approach is we can have a fusion of both of them. So you can have you can cover most of the spectrum within the data-driven approaches, but the outliers which are there, something like where you can see that you have not seen when the experiments were done. So that can be captured as part of the model, and that's why you need to look at a hybrid approach. It's not just a data-driven approach or just a model-driven approach, but you need to have a combined approach, and that's something what we are going towards, like where you cannot know that what the system is going to do, because that's something which is not observed under normal operating conditions. Yeah, no, but I completely agree, and that's something we have looked at, and we are trying to solve that. But it's a very difficult problem to solve. So, yes,
I got a question too.
Yes.
So the model, if it is assuming an ideal component, how do you modify the model or make it more realistic to include the variation from one component to the other? I'm coming from like an industrial engineering standpoint.
Right.
You're making 1,000 capacitors or trying to get it to source it from somewhere.
Right.
There will be component to component variation, serialized. Is that a part of the strategy at all? Is it considered?
Right. So you're right, because whenever we develop a capacitor model or a battery model, it's trying to include. It's not going to include it's not tuned to a specific component, but that's where your uncertainty comes into picture, or your Kalman filter will come into picture. So the Kalman filter, basically the filter will try to go to the near, or it will try to converge based on what type of that component is. But then you have that uncertainty part also attached to it, because the uncertainty will be in the manufacturing process. It can be the way the sensors are used. So you have to include that as part of the model itself. And that is all. We capture that part also. You're right. Yes. So that's why it's not always 100% accurate, but you give a distribution of it. Like probably in the next. That's why I said, like when device is going to fail, if you give an estimate of within a 5% margin or 10% margin, that's something which is acceptable. But if it's like if the device is going to fail in 1 hour plus minus 1 hour, that's not something which is useful. So those kind of things.
Thanks. Do we have any more questions?
Yes.
Brian in the back, just yell.
Hey, yeah, thank you for the presentation.
Thank you.
And one thing I was wondering, so I saw at the end there you had basically a curve fitting model, right, done empirically for characterizing lithium-ion battery, right? I think it was a lithium polymer. So if I had to change slightly change the chemistry, or even like the electrolyte, like if I went to like a solid electrolyte version of that lithium ion, can I expect your model to be useful for that, or do I just have to start fresh and empirically brute force curve fit characterize every?
No, so that's what we are trying to go away from, like not to do a curve fitting or not to use that part. And that's what, if you look at most of the equivalent circuit models, though they do most of the curve fitting part of it, because what you have is you have some data, and you try to estimate the parameters based on these data points, and once you have that, they are fit for that. But the reason we moved from that away from it, because that's why we actually looked into electrochemical model. So that electrochemical model actually captures, so the Nernst equation and the Butler-Volmer, they are the key to any electrochemical reaction happening. So it can be any cell. So that's the reason we try to move. So this is more of a generalized model. So once you have a framework for this, you just need to know what type of cell it is. So if it's a lithium ion or a lithium polymer, or if the chemistry is different, then your equation will remain the same, but the parameters can be a bit different, which can be estimated in a very short period of time. So we have developed, over the period of time, we have developed a way to do that in like you take only certain characterization points, so you don't need to characterize all the batteries, but you characterize only 3 different discharge values, and you can estimate this. So that's we have shortened that process by generalizing the model as more as possible. Yeah, no, you're right, because that happens, and that has happened several times. Like if you fit on a certain curve, you can just estimate, and that's why I was saying that your spectrum, then it's limited only on what data you have, because then your model depends only on that data.
Right.
Yes.
One last question.
So if we stick with this battery one, how many parameters were you monitoring? How many parameters go into the equations?
In the equation, we have 16 parameters we go in the equation. 16? Yes, yes. So currently for the lithium ions, we have 16 parameters. So, but the good thing about using the electrochemical model is it captures the aging phenomena relatively easier than the equivalent circuit model. So we have started using these models now.
All right, thank you.
Okay, thank you so much.
So I'd like to thank you guys all for coming.